Okay, back to this. So basically, understand the mechanical properties of materials naturally. These are all things that we've talked about before. Understand destructive testing, what it means. Non-destructive testing. Basically, two classes, either destructive or non-destructive. You're either going to destroy it or you're not. One or the other. Strength is naturally going to tell you here to withstand an applied load. Doesn't give you anything about percent elongation or ability to indent or anything else. But now we get down here in ultimate tensile strength, sometimes referred to as simply tensile strength, refers to the maximum load carried capacity of that metal. Okay, so this is basically, or the strength at the metal exact point when failure occurs. So this isn't when it stretches or elongates. That's yield percentage, right? That's yield strength. We're going to talk about that here in a minute. Here's when it actually breaks. Okay, so back here. It's necessary to understand that it's meant when a metal behaves elastically. Elastic behavior conforms to the deformation of metal under load. So particularly in order to, here it kind of talks a little bit about it more. Stress beyond its elastic limit, it no longer behaves elastically. Its behavior is now referred to as plastic. Basically, the best way that I could describe this would be, think of a rubber band, right? If you have a rubber band and the rubber band is stretches, and then it always comes back to its normal limit, right? What happens if you stretch it so far, all of a sudden you see the edges and everything starts to crack, then it no longer stretches back to its original limit, then it's elongated. At that point, it's become plastic. As long as it comes back to its original waistband or its original size, think of the elasticity, then that's an elastic reaction. It comes back to its original shape no matter how much it's stretched. But once it's stretched beyond that point to where it can no longer take it, it has grown in size even if it comes back to no stress. Okay. The other thing, you think about Laffy Taffy, right? I mean, you can push it back into the right position, but as you stretch it and it grows, naturally it's becoming a plastic state of frame, or a state of mind, state of size or measurement at that point. Okay. So right here we talk about the point at which the material behaviors change from elastic to plastic is referred to as a yield point. The yield strength, therefore, is at the strength level at which the material's response to loading changes from elastic to plastic. Here's basically a good demonstration of it, saying that and this is a direct linear path, right? Direct relationship. This isn't the case in most materials. So for some of this stuff, it's really important to think about. So I want you to think of a bolt, okay? So let's just take a high carbon steel has a tensile strength, a yield strength of 90,000, but the tensile strength of 140. However, if it's just strong, it's going to be brittle. It's not going to be very flexible as well, right? And we've talked about this in other times as also of what are the properties that we need from this material, okay? Basically, you need to know the tensile strength. And here's the key point. As temperature increases, the strength of the metal decreases. These are always directly proportional. If one goes up, the other one goes down, okay? And the easiest ways to think about it is to think their opposite reaction is, what do we do if we're going to bend a piece of metal? You're going to be able to heat it up, and it'll move, right? It's easier to move once it's heated up. So as temperature increases, the strength decreases. Temperature also naturally, with this same logic, has the same effect on its ductility. Naturally, as it increases, then it becomes softer, right? Okay. Tensile testing. Basically, I want you to read through this. It's going to be able to tell us this. And I want to think about a bolt, right? So if you want a bolt to have a certain yield strength, and I talk a lot about like a rock crusher, I want it to be able to take a beating. It has to be soft on the inside, but it also has to be able to withstand a lot of force and pressure. And if that thing just keeps growing and growing and growing a little bit at a time, then all of a sudden it essentially is going to become plastic. And just like anything else, it gets out there, and it starts getting further out there as it's going around, and it's further and further and further. Next thing you know, it amplifies by doing that, okay? So a good example of this would be a low alloy steel. It's 50,000 yield strength, 75 on the tensile. you know, say we're always stretching or pushing this limit right here, and then eventually what's going to happen is it's going to slowly start creeping out, creeping out, creeping out. And not only that, but dust, dirt, grime, and everything gets behind that, and it starts forcing it out, starts forcing it out. Next thing you know, that bolt just snaps. Okay? So we need this yield strength right here of say 90,000 is important, because it's not going to just keep growing. It's actually going to come back to its right position each time, especially if we're running a lot of high force in there, like a rock crusher. Okay. Talk a little bit about tensile test. You know, you can read through this section on your own. Here's a good example. We do have a tensile machine in the shop now. The opposite end of our bender is actually also a tensile, and we can figure out the entire load of the reduced section, right? So we've got our pressure there, how much force is on it. Our gauge shows us that, and then we'd have to be able to do the cross-sectional area, and by running the formula, it can be calculated, okay? But you got to make sure that it's a nice, smooth area, not a ton of notch toughness or anything else, or no notch indications. So right here it talks about reduced section, somewhere near the center of the length. And that's basically, we want to force it to break within this area, okay? All right. And you're starting to see a lot of my notes that I've taken, I've run into across in the industry, and things that I've had to work with, not only on taking tests, but these are things that I've looked at when I've been writing procedures. You know, here's a good example. You got 12,000 pounds of load of force to be able to break it, but the area ends up being a 0.2 inches squared. For example, 1 tells you, here's the diameter, you know, here's the radius. It lets you work through that entire problem when you're doing that, so you can understand how square surface area can help you calculate this. All right, so once in place, the tensile load is applied at a steady rate. Again, you don't want to be, you know, give it a big jolt or anything else. That's not what we're trying to do. We're trying to do it at a regular, nice, easy, steady, consistent rate with the exact same amount of force. We don't want to do a big jump, big jump, big jump. That has a big difference, and it's also hard to measure. So right here, stress is proportional to strain since it's applied to the load at any time divided by the cross-sectional area. The strain is the amount of stretch apparent in a given length. So naturally, the stress is the force it takes, but the strain would be the actual movement, right? How much is it strained or how much is it grown each time? And it's usually expressed in inches squared. Okay. So typical stress strain curve for mild steel. Let me switch back here to the PowerPoint. You can see a tensile tester. This is a bigger one. However, ours lays on its side, but the opposite end of the bender is actually to where you can put one piece in here, one piece in here, and then and pop it. Okay. All right. Sample preps talks about calculation. Here we're at the typical stress strain curve. We'll go through some of that. Ductility, ability of the metal to deform without breaking, drawn into a wire. Okay. So basically, here it is, right? What they're telling you is exactly this. Here's the amount of load put in, or in this case, you know, we're looking at a stress strain. So now this is our stress. This is how much load we're putting in, 90,000 pounds. And all of a sudden here is where it's no longer going to go back to its original position. Boom, now it's actually deformed at this point. So what just happened is it actually gave. It was holding that load, and then all of a sudden it opened up. It can no longer go back to its original shape. Okay? So now sometimes at this point it can still take more force. You notice, not a lot more force, but it grows very drastically until all of a sudden it comes to its reduced section. Not everything looks exactly like this curve. I'm going to be honest with you, most of the ones that I've done have hit like this, and then they actually kind of just flatten out, and then they go do it like a really sharp, and then all of a sudden just drop. Okay? So this is a really ductile piece right here, because you can see it's got a real nice arch as it's going. Otherwise, it would just come across, and a real brittle piece will just drop off here at the end. Once it's extended, it's done. So this is the upper yield point, this is the lower yield point, and this is the percent of elongation, okay? Or point of elongation at that point. How much has it gone before it snapped? So this is total, sorry, I'm going to take this back. This is total elongation, okay? But you can measure this on a graph, And we had a machine at the last place I worked in Wyoming where it would actually graph this entire thing for us. The computer would do it, but of course it was about a $200,000 machine. I shouldn't say that. I think it was 100. But it's pretty cool. Anyway, the slope is the modulus of elasticity. So the slope is the modulus, right? Young's modulus, it's saying how much force, how much it grows. And at that point, it's still an elastic piece. Talks about it here. Eventually, the strain will begin to increase faster. I think we've kind of made it understandable. So right here, drops to some lower limit. Talk about ultimate tensile strength. So for less ductile metals, there may not be a pronounced change in behavior. Again, usually it doesn't have this big long swoop. It just breaks and drops off at that point. Okay, here's a couple of pretty good examples. This is an engineering stress strain diagram. So one of the ways that they can start to do this before actually measuring it. Now, of course, it's much easier. But they would do a 2% curve, right? So you would take this, you would offset this curve of what you knew. You'd go for 2%, and that's roughly where you could figure out where the yield strength was. So say you wanted something to break at 90,000. That's where you would want to calculate. You could take this material and you were to stress it, say, oh, okay, just off a normal machine, I could plot this, right, without having the computer graph and everything else. I could plot where all these things happen, just like we do in our materials engineering course with Bruce Emerson. And then we can come back and we could draw that plot, or that curve, and we can say, let's take that 2% here. That's going to be our yield strength. And that's what we need to shoot for, okay? Basically, it talks about their common offset is 0.2% of the strain. And then toughness is a measure of a metal's ability to absorb energy. When I think of the definition of toughness, I think of a boxer, and I think of getting punched. And the reason I do that is because exactly, if you read that, it makes perfect sense of how to keep these things straight. Toughness is its ability to absorb energy or to take that punch. And whether it be metal on metal, rock on metal, or anything, even pressure and fluid, of even just the normal dirt, makes a big difference, okay? Following the actual tensile testing, it's now necessary to make a determination of the metal's ductility. This is expressed in two ways, percent elongation and percent reduction. All right, so we'll talk a little bit about that. Basically, I'm going to come in and I'm going to put 2 marks here, right? So I'm going to do 2 inches in between. I'm going to put a center punch. I'm going to stress this thing until it breaks, and I'm going to put it back together, and then I'm going to remeasure it. And at that point, it come out at 2.6. So final length original, 0.6, 30% elongation, okay? The other thing I can do is on this one, on this piece right here, is I now have a true diameter piece, right? So I'm going to break it and stretch it. What if that drew down to like a 1/16 of an inch diameter? I can measure it in a cross-sectional area as well, okay? And it's good to do it in both so you get a good comparison. All right, so here's percent reduction of area. It's the same thing. If it's a half by half, whatever, or the diameter example that it gave us earlier over on the other page. Okay, read through this. Metal's ductility is directly related to its temperature. And this is also really important when you think about the service condition again. Okay. At this point, I'm going to stop and take a little break. Well, let me come down here and let's talk a little bit about brittle since we're here. So here's a good example. These are actually Sharpie V-notch tests, okay? So the one on the left is very brittle. As you can see, it's a very straight shoulder, 90 degree. And then over here, we've actually got these tiers, right, of layers and stuff like that. It was broke from the same edge, but you can tell that it actually gave, instead it just snapped in a nice square edge, it actually elongated some before it snapped. So the left-hand side is brittle, right-hand side is ductile. Now this can be actually done, this could be the same piece of material, but this could be done at different temperatures. And we'll talk to the brittle to ductile transformation temperature here in a few. Here we're going to talk a little bit about ductility, differences in magnitude versus the direction in which the load is applied, and also the rolling of material, or the rolling direction, which I've got a short note on here. X direction is in this way, right? So think of this as a flat bar, our 3/8 by 6 rolled out like this. That's going to be the strongest. The Y is going to be our next because it's been compressed. And then our Z, our through thickness, is actually our weakest point at this point, all right? Because the grains grow differently.